Rolling down a ramp. I have an object on a ramp. It rolls down. How to find its acceleration? How to find its mechanical energy? How to use conservation of mechanical energy for this object? Okay, let's start with the concepts of spinning, slipping, and rolling. The first object is a spinning. It doesn't have any translational motion. The second is just slipping without any spin. The last is rolling, means that it does have spin, it does have translational motion, but it doesn't have any slipping. Means that the bottom point of the object, which is always in touch with the ground, doesn't have any relative motion to the ground. It's always at rest relative to the ground. It's very important. Okay, let's go back to spinning. In the spinning case, every point on the object, regardless of the distance to the center, will have the same omega because this is a rigid body. But speed is different, linear speed, because linear speed, is related to omega like r omega. Depending on the r, they may have a different speed. Maximum speed is for a point on the circumference of the circle. Let's consider the topmost and the bottommost points, okay? The topmost will have this velocity of r omega rightward, the bottom point leftward. Equal but opposite, okay? The other points, r is the radius of this spinning object, okay? But it also could include other points like this, not necessarily on the circumference. Anyway, they have their own velocity. For this point, for example, it's downward. For the other symmetrical points on the other side is upward. Every point has a symmetrical point relative to the center that cancels its velocity, So for a spinning object, let me show you on the blackboard. For a spinning object, okay, for every point like M, relative to the center, we have a symmetrical point like N. They have always the same speed but opposite velocities, V and V. They cancel each other. Okay, this is why the object doesn't have any translational motion. The slipping case is very easy, understandable for you. It doesn't have any rotation. So all points on the object, all points here, 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 will have the same rightward velocity. Okay, same. For the rolling object, the case is a little bit different. For the rolling object, first let's consider center of mass. Center of mass of this circle, let's say it's moving at a speed of v or v naught, rightward, okay? This point is very important for us because translational motion is considered based on the center of mass, okay? But if you consider other points, they won't have pure just v naught translational motion. Because of the spin and their distance to the center, they will have an extra term. Extra term, I mean, for the topmost point, the velocity of the point is v naught plus r omega. R omega inherited from the rotation, v naught inherited from the translational motion of the center of mass. Okay, we have an addition on the top. Of course, for a point like this, we have the same thing, but r is different because it's closer to the center. We cannot use this r. Okay, it might be smaller r. Okay, but for the bottom point, as I mentioned here, as the object at the bottom point is always in a steady state relative to the ground, is in touch without any slipping to the ground, it is always at rest. They cancel each other. And it's very important. The bottom point doesn't have any translational motion. So the whole body has a translational velocity like v or v naught rightward, but the other points, depending on their location, may have larger or smaller, let's say linear velocity, okay? That's all. For the rolling, we are done. And let's go to the rolling and the kinetic energy. For an object in rolling case, rather than a half of mv square, it's just because of the translational motion, you know that we have an extra term, a half of I omega square. I is the moment of inertia and omega, it's the angular velocity. Okay, so basically the kinetic energy is always including a couple of terms, one related to the translational motion and the other related to the rotational motion. Now consider an object rolling down a ramp. At the beginning, let's say the object has an altitude of h relative to the ground and it's at rest, okay? So the energy is just potential energy, gravitational potential energy, mgh. It rolls down and gets a kinetic energy. Kinetic energy is supposed to be a half of mv square for translational motion and a half of I omega square for rotational motion. I put them equal and then we are done. We will use this equation for the upcoming questions and we'll have more practice. Okay, this is how we deal with the rolling down a ramp. And also we will have a practice shortly for finding the acceleration of this object, the linear acceleration. So let's proceed to the next question. You will learn it. A round object of mass m, radius r, and moment of inertia I rolls without slipping down an inclined plane that makes an angle of theta with the horizontal. Something like this. Draw a diagram showing the forces acting on the object. What do I mean by this diagram? It's actually the very famous free body diagram. Let's say this is the center of mass of that object. What are the forces? First, downward force of mg, weight. The other is the normal force that the ramp exerts on the object to hold it on the ramp. And the other is the friction. Which kind of friction? Static or dynamic? Yes, static. Why? It's rolling without slipping. Means that the bottom point of the object in touch with the ramp is always at rest relative to the ramp. So it's not dynamic friction, it's just a static friction. Something like this. What this static friction is doing there? This static friction is making torque. This is a static friction tangentially acting on this rolling object. And then this is the radius and it makes a torque. And this torque is exactly the reason for angular acceleration. The rolling down object gains. It's very important. Part B. Derive an expression for the linear acceleration of the object. Linear acceleration of this object, A. Okay, how to find it? Let me first remind you something about the usual way we use for not rolling just a slipping object on the ramp and then go back to this case. Okay, let's consider something like this. I have a ramp and a box on this ramp like this without any friction. Forget about friction. This is the theta, the angle the ramp makes with the horizontal, and here I have mg. I'm going to decompose mg to its components. You know, this is theta, this is mg cosine of theta, the component of mg normal to the ramp, and the other is the other component parallel to the ramp, is in charge of accelerating the object, mg sine of theta. We have no friction. Okay, forget about it. Then we can use F net is equal to ma. This is the Newton's second law. And then mg sine of theta is equal to ma. And then acceleration is g sine of theta. This is from previous lessons we had already in dynamics. Can we use it for rolling down object? Not exactly. We should have some more additional terms. Look at this object. First, I decompose mg and again remind you the mg sine of theta. Okay, so far we are okay with that. But if I use Newton's second law, I mean F net is equal to ma. F net is mg sine of theta minus Fs. Because we have an opposing force like Fs against downward force of mg sine of theta. They fight. So we have a combination of those. Mg sine of theta minus Fs is equal to ma. Let's divide both sides by m to get rid of m, the left side of equation, and purely have acceleration. G sine of theta minus Fs divided by m. I think we are not done yet because I should get rid of fs. I should convert fs to the noun values like I, like theta, like gravitational acceleration. So let's get rid of that. How? Do you remember I told you something about the torque? Here we have fs, the radius of the rolling object, and I told you fs will create a torque. Newton's second law in rotational motion is torque equals I alpha, you know. On the other hand, torque is created by this fs, is force times distance. I can put them equal. Yes, it's very important. Then I can rearrange the equation and find alpha to be Rfs divided by I. Then look at this. You know linear acceleration is always r times angular acceleration. You know that, okay? So why not we can use it here? How? Here, look, r alpha. I can import the alpha and then write it as r times rfs divided by I is equal to acceleration. Then I can purely find fs based on the given quantities like I and our goal, acceleration, and also radius of the object. Now we can get rid of fs. So here I substitute fs for this and find this relation. Okay? Then finally, I can go one step more and solve this equation for a, because on the right side also I have acceleration. I should take this term to the right, to the left, and then solve it for acceleration and find it. It is not that difficult, you can find it. Acceleration is g sine of theta divided by 1 plus I over mr square. Let me just consider this equation in more detail. Let's say the object doesn't have any revolution, doesn't have any rotational motion. So I disregard the I, forget about the I. If I exclude the I, this term is gone, so acceleration will become g sine of theta, something that we always expected. Okay, done. But if we have something like I, the moment of inertia, the case is getting more complicated. But what about the I? Okay, I depends on the shape of the object. Let's consider them here. For a solid sphere, for a solid cylinder, or for a loop or a hoop. Okay, for a solid sphere, I, we had this lesson, is equal to 2 over 5 mr squared. Let's plug in the values, and then acceleration will become 5 over 7 g sine of theta. About the cylinder, I is a half of mr squared. If I plug in this I, this equation, I will get 2/3 of g sine of theta. And for a hoop, a ring, okay, we have I is equal to mr squared. Then plug in this mr squared, and it's very interesting. It's a half of g sine of theta. So for a ring, acceleration is half of the expected acceleration for a box that doesn't have any rotational motion. The box had an acceleration g sine of theta, you remember. Now it's a half of that. A half because, anyway, the rotational motion comes to play. Another question. A solid cylinder rolls down an incline that makes an angle of 5 degrees with the horizontal. The cylinder starts from rest and travels a distance of 1 meter measured along the plane. Okay? Determine the final linear speed of the cylinder. Linear speed. First, by using the kinematic SWAT equations and for uniformly exerted motion. Just I've reminded the acceleration we found it for a rolling down cylinder, solid cylinder, acceleration is 2/3 of g sine of theta, according to the previous question. Okay, how to do that? Look, Here I have a ramp, an angle of 5 degrees to the horizontal. I deliberately exaggerate this 5 because the 5 is very small. I can show that with an exaggerated angle. And then this is the rolling down cylinder coming down, and the distance traveled, let's say this is x, is 1 meter. Okay, so I can use this very famous time independent equation: final velocity squared minus initial velocity squared is equal to 2ax. Okay, a is here, I know the a, just I plug in the values and then find the velocity. Initial velocity, it starts from rest. Okay, so rest is here. Okay, so it's 0. Actually, v is supposed to be a square root of 2ax. Okay, here I have no very complicated cases to be reminded. This is g. Okay, this is sine of theta for here, and then this is the distance traveled on the ramp, x, that's given to be 1 meter. So we are done. This is the final velocity, 1.1 meter per second. Okay, the double I case, by considering energy changes of the cylinder. Okay, energy changes is a little bit longer. Here we have mgh, the total potential energy on top, is equal to the total kinetic energy at the bottom. Okay, you know that, I told you. Then let's substitute the I. For a cylinder, I is a half of mr squared. You see this a half of mr squared related to the cylinder. And here omega is supposed to be v divided by r. V is exactly the final translational linear speed, okay? And r is the radius of the cylinder. You know, v is equal to r omega, so omega is v over r. We have used this here, okay? Then let's proceed for to summarize all of them, the two terms, in 3/4 of mv squared. It is not that difficult for you. You know, all terms have m and v squared, just we combine them. H is 1 times sine of 5 degrees. Why is that? In this triangle, this is theta, this is h, and this is hypotenuse, x, okay? Sine of theta is height divided by hypotenuse, x. So h is supposed to be x sine of 5 degrees. And the distance traveled on the ramp is 1. So it's 1 times sine of 5. Okay? Here I can drop the mass. I cross out the mass. I have g sine of 5, gh actually, and h is 1 times sine of 5. 3/4 v squared, the remaining part on the right side. Okay? And then solve it for the v. V squared is supposed to be 4/3 g sine of 5, and then I take a square root. That's all. And I have taken the g to be 9.8, more realistically. The velocity will be 1.1 meters square, parallel to the ramp. Okay, same answer, but what's the benefit of this, or the advantage of this approach? The advantage is, in this approach, you shouldn't know necessarily what's the acceleration of the linear acceleration of the rolling down cylinder, because in previous part, look at this, in previous part, you remember, we started from a background of having acceleration to be 2/3 of g sine of theta. Here we don't have to. We can start from the scratch. This is the benefit. Okay? A solid sphere of the same mass, also change the object. This solid sphere now as the cylinder. So this is a sphere, okay, in this case, and it was already a cylinder. Rolls down the same inclined plane, same thing, okay, starting from rest. So they have just replaced the cylinder for a sphere. Same mass, same radius. Explain which of the objects has a greater rotational kinetic energy at the bottom of the plane. Okay, let's go back to this. You remember when I used this conservation of mechanical energy, here I had a term for I. You remember, okay? This very important term because it's highly affected by the shape of the object. If I replace it for a cylinder, for a sphere, here I have 2 over 5 mr squared because I for a cylinder is different, is this, okay? Then I will solve it. Just compare them, a half of mr squared and 2 over 5 mr squared. Which one is larger? Yeah, cylinder has larger I. So moment of inertia for cylinder is larger than a sphere. Okay, now let's continue for that. Here we have at the top, we have just a potential energy, same potential energy because they have the same mass, mgh, and it's released and will become kinetic energy. This kinetic energy has two terms, a half of mv squared and a half of I omega squared. Okay? Here, this kinetic energy is distributed between two terms. If I have larger I will expect larger term for a half of I omega squared and a smaller term for a half of mv squared. Okay? And vice versa. When I replace it for a sphere has less moment of inertia. So this is going to be smaller, and then a half of mv squared is going to be larger. So if I replace it for a sphere, I expect larger speed, larger linear speed at the end. I can start like that. The total kinetic energy of each object is the same. Why? Because they start from the same potential energy on the top, okay? But it is distributed in different proportions between translational and rotational components. I mean a half of mv squared and a half of I omega squared. Then I can continue like that. The sphere has less moment of inertia, I told you. So less rotational kinetic energy. So larger linear kinetic energy. That's all. This is a very scientific answer I can have for part B. Thank you for watching this video and thank you for your kind attention. Take care. See you soon.